Okay, this is the next in this series of the videos, the guides that I'm going to do for the workbook, just some limits and delimits. This isn't a comprehensive account of how to do a descriptive statistical summary, but it is sufficient for your workbook. I'm going to use the practice seminar data, which was originally from an MSc that I did several years ago. You clearly are not going to use that because you need to use the workbook 2 data. A couple of you have reported, and I noticed in the seminar, that you struggled to just go straight into SPSS. This is how I would do it. I'd download the data set and then I would just click on it and SPSS pops up ready for me. But a couple of you couldn't do that. So in that case, what you do is you just download the data set and then open up SPSS independently and then search in your downloads, and then you can open it that way. As we've seen in most of the seminars, you've got the same data set that we've been using for practice for most of it, with the variables nicely arranged. This is all ready for you if you want to practice. Perhaps the research question that I'm going to be concentrating on today is preparation of a data set to see whether BMI is correlated with the BREC2 data. Now, the BREC2 is a questionnaire, and as you can see, I think somewhere, yeah, we've got a -1 in there. So it does go minus. There's a -12 in there too, just giving it a quick scan. And then BMI is as you would expect. With the BREC2 is a measure of self-reported motivation towards exercise, behavioural regulation in exercise questionnaire version 2. There is a more updated version, but it doesn't give us this RAI, this relative autonomy index that we're interested in. So the research question might be something like, is BMI correlated or associated with self-reported motivation to do exercise? You would expect that it would be, so I would proceed on that expectation. So my hypotheses for this would be that my experimental hypothesis would be that there will be a strong or a positive correlation. Do I mean positive? No, I mean a negative correlation. As BMI reduces, then I would expect motivation to go up. So I would expect to find a negative correlation. But I'd expect that to be quite strong. The null hypothesis, which is always the one that we test when we're doing statistics, would be there would be no correlation. So I'd proceed on that basis. First thing to do, and that's the purpose of this, is the descriptive statistics. This video is I would explore these two data sets. So first thing I'm going to do is produce the descriptive statistics in a table. So we get frequencies. We're going to have to do this. We're going to take BMI. We're going to take just click them across. Statistics. Mean. I want the median. Not too interested in the mode, mainly because I'll tell you in a minute. Excuse me. Places we're definitely interested in because we're testing whether or not this is normally distributed. I'm interested in the minimum and the maximum simply, again, because that is a good guide to how to, whether I've got some weird data in there. And then I'm interested in the standard deviation because I want to compare that to the mean. So that's enough for statistics. I'm interested in the chart. I want to hit, and I do show the normal distribution curve on there. I don't want the frequency tables because they're boring. Okay, and we get our two tables. Sorry, one table with the two data points. We've got 75. The mean and the median on both seem to be, well, let's take them one at a time. BMI. Knowing what I know about students, the mean is 26, which is just over into overweight, but most of these people were athletes, sports students, so we'd expect them to have a high muscle mass. So it's not too strange at face validity that their BMI is quite high. we've got standard deviation of 4, which isn't very much. So that means that the mean is 26.5. And on average, the majority of the people are within 1 standard deviation, and that takes us down to 22.5 and up to 30.5, and that's kind of fine. And then we look at the maximum and the minimum. The minimum is 18.4, which is fine, and the maximum is 37, which is quite heavy. The BREC2, we will look at that before I start concentrating on the skewness and kurtosis. Once again, mean and median not too far apart. Because the median is slightly larger, that's going to tell me something about the expected direction of skewness, just a subtle hint in there. Standard deviation 15, so once again, standard deviation is comparatively low, especially given that we know that the scale of the BREC2 goes into negatives as well, so it's not starting at 0. Skewness and kurtosis in there, and the minimum and maximum makes sense. Right, let's have a look at so what I think is best to do, and what helps you explain things and understand things really well, is if you try and make up your mind what you think you're going to see. So BMI, we can see here that the skewness is positive, kurtosis is negative. So negative kurtosis means it's going to be slightly flat, ever so slightly, because it's a low number. And the skewness is going to be positive, so we're expecting maybe a large data, which is probably about 37. So you can begin to get a sense of the picture from the statistics. And here we are, slight positive skew, maybe caused by these two people, slightly flat, but never mind. Because we've only got 75, there's a data point here. Incidentally, I think I said this before, you can constrain an SPSS by going into various options what the buckets are here, down there. It does it mathematically according to the data set you present it, but you can constrain it. Here it's quite intuitive. You've got 15, 20, and it hasn't gone into decimals. And the BREC2, I should have looked at this. We've got negative skew, and expecting something a little bit pointy. And yeah, you can see from here to here, it's not really fitting the normal distribution that well, because we've got 2 down here. So we might need to think about, okay, if I'm going to look at a correlation and look at parametric assumptions, and in that case I'd be choosing between the Pearsons and the Spearmans, then perhaps I would want to remove those, but we will see. Okay, so to proceed from there, the next thing I would tend to do is look at box plots. The next thing perhaps to do is to get a calculator. Now, if you want the official way of calculating skewness and kurtosis, you're going to have to do something. Don't worry too much about it, but you want something called a Z test. And all that means for you is you have to take the kurtosis and divide it by the standard error of the kurtosis. Don't worry about why, it's just a process. So we're going to 0.285, and that's a negative, divided by 0.277. And this is okay. Remember, we've spoken about 2s. If it's within plus or minus 2, what you're really looking for is whether it's in between plus or minus 1.96. And what that test tells you is whether or not your distribution, your data distribution, differs significantly from a normal distribution. And if it does, then your data are not normally distributed, and that means that you should not proceed with parametric assumptions without some sort of treatment for your data. Here, our kurtosis for BMI, this is okay, and let's just explore. I did that wrong anyway, didn't I? Because I've taken the standard error of the skewness and applied it to the kurtosis. So why don't you just forget about the last couple of minutes, and we'll do that again. So 5.9 divided by 0.277. Yeah, and we're starting to get slightly dodgy stuff, but we might be able to deal with that in a bit. Let's just wait until the box plots come up. So I would say that's just outside. Is it massively outside? No. And on balance, I would probably continue. I would probably do both a parametric and a non-parametric and just see how they matched up. Just to look at this, kurtosis. So we had 285 minus divided by standard error event, which is 0.548, which is fine. Okay, so our kurtosis is fine, but our skewness is not. It's slightly too positively skewed to be called a normal distribution, but only just. We'll do the same again with the skewness for the break 2, and that is easy thing to do is to decimal and the plus or minus and put an 8 instead of a 7, so let's just cancel that. Point 0.277. And once again, this is quite bad. So both of them seem to be quite skewed, which officially would point us towards, as if we didn't alter anything, that would point us towards the use of a Spearman test, as a non-parametric rather than the Pearson's. Let's just do the kurtosis. So I'd expect 1.6, which is quite a big one anyway, divided by 0.548. Yeah, quite large too. Right. All is not perhaps lost. So what we do next is we look at the box plots. And why do we look at the box plots? Largely it's to back up our impression of the data, to give us another representative graphic of it, but also for a couple of other reasons. So box plots. Drag that up there. And let's look at BMI first. Y-axis. And just as it stands, just as it runs, we've got a box plot that looks quite nice. Okay, it matches what we'd expect. No outliers, so that's one of the major reasons why we'd use a box plot, is to identify outliers. So we've got a reasonably tight data set there. It's 75 people, which is quite high. Just incidentally, if you are collecting data points, you really want to be looking, in an ideal world, to get up to 500. And the reason for that is when you're using smaller numbers, you use a different kind of distribution called the t-distribution. Once again, this is not something you need to go into, but 500 is where the t-distribution and the normal distribution kind of look the same, or almost inevitably. Having said that, if you've got 100 data points, then they're looking the same enough. So 100 would be seen as kind of a minimum number for quality. Any less than 20 or 25, and you're really looking into very meager data sets. So perhaps you should, if you've got any less than that, you shouldn't really be doing parametric tests and assuming normal distribution. Let's look at stay with BMI, because this is another thing I tend to do, and especially when you're looking at a correlation, and I'll cover this in the next video, which you can look out for, is I tend to, you would assume that the BMI distribution for males and females would be different, and I just want to see visually whether that's the case. And it is. So what we've got here is we've got a couple of outliers on the girls. We've got, I think it's 1 that's girls. So 0 is boys, 1 was girls. Boys look relatively normal, somewhere between just above 20 up to high 30s. Now the girls, much tighter, just below 20 up to approaching 30. But then we've got to what I'm assuming are much more muscular girls, and they count as outliers. But these overlap, which is probably why we saw a nice a nice box plot for both of them combined. In this case, you could look for differences between the two, but according to this, I would probably say it's fine to proceed just with a kind of rough rough correlation. That's fine to do. Next one is graphs. Chart builder. Just going to this one out and look at my GPAT. Fire over, and we see we've got a lot of outliers here. We weren't looking at GPAT. Well, let's just look at the thing that we were looking at, which was BREC 2. Here's BREC 2. So we've got a couple that are quite low. Now, given what we know about the BREC 2 and that we had some odd skewness and kurtosis going on there, I'm quite interested now, having seen these, as to A, let's just chuck it in there. And we've got quite nice data sets, but we've got one highly unmotivated lad and one highly unmotivated lad, so 58 and 70. And what I'm wondering, given these data, is if we cut out both of those and then redraw our histogram, if we cut out both of these, I'm assuming that's these two, that we might end up with something a bit more normally distributed, and then we could proceed with a more powerful test, given that the distribution for BMI wasn't so horrifically outside the correct bounds for skewness, just a little bit, as you would say here. So what I'm going to do is I'm going to hop over to the data, and it was 58 and 70. So go down to 58. It's the -12, and we're just going to cut that. And what we are also going to do is cut out number 70, only because we've cut out number 58. 70 is now 69, and that is the -1. Okay, and just let's draw descriptive statistics, frequencies. Let's just do that again. Looking at so it's removed these, and I'm really interested now as to whether that's brought down, or it's clearly going to bring down the skewness and kurtosis. It won't have adjusted, well, it might have adjusted the BMI too, but that's jumping the gun. So what we've got to do is a little bit of calculator work, getting it right this time. So 0.671 divided by 0.2 equals 2.3. That's actually made it slightly worse, but it is what it is. And then kurtosis is 0.378 minus divided by 0.5. Okay, and that's still within normal bounds. What we're really interested in is what happens to the BREC, though, because they're the two values that we've removed. 0.093, which is a minus. Well, it doesn't really matter because we're dividing. 0.281 is normal, and 0.565 over 0.555 is normal. Okay, so we've kind of normalized the BREC to, on balance, you would potentially say that it's therefore the correct decision to have removed those two from the data set. What you can't, though, do is then search out all the light people from the BMI or the heavy people from the BMI. If you were doing this as part of screening, where you only really wanted a tight data set, then perhaps you could justify it, but you don't really want to be selecting out all the data, because you're just ruining what the results are. The whole idea of science is that you decide a priori in advance what your research question is going to be. You justify your method, and then you run the test, and the data are the data, rather than you pick and choose. Okay, so what you have now is the descriptive statistics. The only other thing you might want to do, given that I've done this under the assumption that we're going to come up with a correlation, is I would want to run a scatter plot. So chart builder, just a simple one. Gender code comes out, and BMI goes in. I'd expect BMI. It doesn't in a scatter plot. There's no causality inferred. So you can put either one you want really on the X and the Y axis. Of course, if I was doing a column graph, I would want something categorical, or the predictor value on the X axis. I'm going to click OK. And doesn't look to be a strong correlation. So always run the scatter plot without the line first and make up your own mind what you're seeing. Always pay attention to the scale, because quite often SPSS will draw it as is and make up its own mind. So if there are no data points outside this little window, then SPSS won't necessarily start at 0. So it zooms in, and that can sometimes give you a little bit of a false picture. And the last thing to do is to see whether the graph. So I actually think if I had to draw a graph through here, it would probably be towards the 80-ish, down towards the 40. Let's see what happens. No, wrong. We have got a negative line. That doesn't mean that we've got a negative correlation. However, that's really getting beside the point. The most important thing is that you now know how to screen your data. Just to go through it in order. Before proceeding with any inferential tests, you must do some form of descriptive statistics, otherwise you'll make bad decisions. Point 1 is comment on the difference between the mean and the median. Point 2, comment on the relationship between the mean and the standard deviation. And you can look at the skewness and kurtosis and use the maximum and the minimum, maybe, if you are interested in whether or not there is some errors in there. You draw histograms for both of them to having made up your mind what you expect to find, and then you compare what you find in the histogram to here, to the numbers, and you also compare it to what you'd expect in real life. Not lastly, you would then go on to the box plots. If you're interested in correlations, you might want to split that out by gender. If you're after differences, you probably wouldn't, because the differences might be between males and females. And on those box plots, you're actually looking for outliers. So that's the GPAC. This is the breadth, the initial breadth. What you can use the box plots to justify the removal of outliers, and also the identification of extreme outliers, which you definitely want to know about because they might be errors or false reports. Incidentally, if they're extreme, they're reported as a star rather than put into the graph, simply because if it, let's say we've got -20 up to 80, if we had one that was -1000, then this bit of the graph would be so small that you wouldn't even be able to see the box plot. So SPSS preserves your ability to see the actual majority of the data, and if it's beyond what it can realistically fit within a window, it will just star them and tell you the number. If you see a star next to it, unless you've got a very good reason, you might want to think about reducing taking that out of your data set. Because this was a correlation, I then did a scatter plot because it's looking at the relationship between two variables. Incidentally, if I was looking at a difference, I would have drawn a column graph. Might as well do that now. Just thinking about a different question, I'm interested in whether there is a visual difference between boys and girls, males and females, on their motivation, because we've already looked at that. So that's already in place. In this case, simple column graph, gender code on the x-axis because that's categorical, and then the count, I don't want the count, mean break. Okay, incidentally, as I said before, you can change the statistic on the break or on the y-axis here, so you can have median or mean or several others. Just plot that. And here's your column graph. You've got gender code, you've got males, you've got females. It appears that females are slightly, or report being slightly more motivated towards exercise on the Breck scale than males, and you can see the visual difference here. Last thing, as I said, back in the lecture in week 6, always check when you've got computer-generated graphs that it starts at 0. If this started at 40 and finished at 50, it would look like a really big gap if you hadn't paid attention to the fact that it had started at 40. Because this is starting at 0, we can see that the gap isn't so huge. And perhaps we wouldn't expect to see a significant difference there. Okay, that's the end of this little guide. As I said, it's not hugely comprehensive, but it does tell you how to get sufficient grades in your workbook and also take you through the processes using SPSS.